Imagine you're floating in the calmest place you can think of. The emptiest part of space. No wind, no sound, no up or down, just darkness and distant galaxies. Now here's the unsettling part. Even out there, on the largest scales we can measure, our entire neighborhood of galaxies is moving. Not slowly, not a gentle drift. We are being pulled through the universe at hundreds of kilometers per second. And we don't mean the Earth orbiting the Sun. We don't mean the Sun orbiting the Milky Way. We mean the Milky Way, the Andromeda Galaxy, and countless nearby galaxies, all sliding in the same direction, as if something enormous is tugging on the cosmic map. Astronomers gave that something a name that sounds like a movie title: the Great Attractor. It isn't a planet. It isn't a single monster black hole sitting out there like a drain. It isn't one object you can point a telescope at and say, "There it is." In fact, for a long time, the area of sky where this pull seems to come from was hard to study in visible light because our own galaxy sits in the way. Dense stars, thick dust. It's like trying to identify a distant city while staring straight into a fog bank. So how do you discover something you can't clearly see? You follow the motion. You measure the drift. You look for patterns that are too big to be coincidence. In this video, we're going to do 3 things. First, we'll prove the pull is real, using a cosmic reference point that doesn't care what we think is out there. Second, we'll track the direction of the flow and show where the Great Attractor hides. And third, we'll answer the big question: what is it really? Because the deeper astronomers looked, the more surprising the Great Attractor became. And by the end, you'll understand why this isn't just a mystery thing out there. It might be a clue that our local universe is part of something even larger. If I say, our galaxy is drifting, the next question is, drifting compared to what? The universe gives us a reference frame. An ancient glow left over from the early cosmos, still filling all of space, the cosmic microwave background. On average, it's incredibly even, but when scientists measured it precisely, they found a subtle two-sided pattern. One direction is slightly hotter, and the opposite direction is slightly colder. That isn't because space is warmer over there. It's because we're moving. When you move toward a source of light, the waves get slightly squeezed. When you move away, they stretch. So as we rush through the microwave glow, the light ahead of us is compressed, and the light behind us is stretched. That hot-cold split is called the CMB dipole, and it acts like a cosmic speedometer. From that pattern, we can estimate our motion through space, hundreds of kilometers per second. About 370 kilometers per second for our solar system relative to the microwave background. Now here's the key. This isn't just the universe expanding, where galaxies separate because space itself grows. This is extra motion on top of expansion, motion caused by gravity. Astronomers call it peculiar velocity, meaning the part that doesn't belong to the general expansion. And gravity leaves fingerprints. If you measure enough galaxies and find many drifting in the same direction, it usually means there's more mass that way, more gravity, even if the view is blocked by dust, distance, or darkness. So the dipole tells us we're moving. The next question is bigger. Are our neighboring galaxies moving with us? Because if they are, then this isn't random motion, it's a cosmic current. And we're flowing toward the Great Attractor. Here's the tricky part about proving a pull in space. The universe is expanding, so almost every galaxy is already moving away from every other galaxy. That's normal. If you only look at a galaxy's redshift, how its light is stretched, you mostly see expansion. So astronomers do something smarter. They measure two things. One, how fast a galaxy seems to be receding, its redshift, and two, how far away it truly is, its distance. If you know the distance, you can predict how fast it should be moving away just from expansion. Any leftover difference is the galaxy's extra motion, its peculiar velocity, the part caused by gravity. But how do you measure distance to a galaxy millions of light years away? You use cosmic yardsticks. Sometimes it's a type of star or explosion with a known brightness. Sometimes it's a galaxy rule of thumb. Big spirals rotate faster, and that rotation relates to their true luminosity. If it looks dimmer than it should, it's farther away. If it looks brighter, it's closer. When researchers started doing this for many galaxies around us, a pattern appeared. Nearby groups weren't just drifting randomly. Whole regions were sliding in the same general direction, like leaves on a river. Our local group, the Virgo region, and clusters beyond were all being nudged toward a patch of sky in the constellations Centaurus and Norma. That's what people mean by a bulk flow. It's not one galaxy falling, it's a large chunk of the local universe sharing a motion, as if the gravitational landscape slopes downward that way. And the more they mapped it, the stranger it got. Because when you point normal telescopes toward that direction, the view becomes crowded and messy, not because there's nothing there, but because we're looking through the thick, bright disk of the Milky Way itself. Astronomers even have a name for this blind spot, a huge portion of the sky where dust and stars hide what's beyond. So we have motion pointing to a target, and a target hidden behind our own galaxy. Which raises the obvious question. If the Great Attractor is real, what's actually sitting behind that curtain? And is it massive enough to pull on entire clusters of galaxies? At this point, most people imagine the Great Attractor like a cosmic monster, one giant object out there, swallowing everything in a straight line. That idea is wrong. The Great Attractor isn't a single thing. It's a region, a wide area of space where matter is more concentrated than average, creating a gravitational slope. If you could see gravity like a landscape, it would look like a valley, and our local galaxies are sliding downhill toward it. So what's inside that valley? Clusters of galaxies, massive ones. One of the key suspects is a dense cluster called the Norma cluster, also known as Abell 3627. It sits in the same general direction as the flow, and it's packed with galaxies, hot gas, and, most importantly, dark matter. Even if you can't see all of it in visible light, the gravity doesn't care. Mass is mass. This is why the Great Attractor confused astronomers for so long. When we say it's hidden, we don't mean it's invisible. We mean the Milky Way makes it hard to survey. Imagine trying to count distant city lights while staring through a blinding stadium spotlight. You can still detect the city, but only if you use the right tools. And here's the deeper twist. The Great Attractor is not the edge of some cosmic drain. It's part of a much larger structure, a network of clusters and filaments that our galaxy belongs to.
Onward to Norma.
In 2014, astronomers used the motion of thousands of galaxies to map our local flow lines, like tracing raindrops as they run downhill. The result was a new way to describe our cosmic address. Laniakea is what they call our local supercluster region, not because it's a rigid wall of galaxies, but because it's the basin of attraction our neighborhood flows within. And the Great Attractor sits near the heart of that basin, like the lowest point in the valley. So the Great Attractor isn't a single object pulling us like a hook. It's the center of a gravitational watershed, and we're one of the streams. But now comes the question that makes this story even bigger. Is the Great Attractor the main source of the pull, or is it just the nearest bend in a much larger cosmic river? So if the Great Attractor is a real concentration of mass, why did it feel like a ghost story for so long? Because the universe didn't hide it. We did. From Earth, we live inside a galaxy shaped like a glowing disk. When we look toward the Great Attractor's direction, we're looking through that disk. Billions of stars, clouds of dust and gas that scatter and block visible light. In ordinary telescopes, the background universe gets washed out, like trying to see a distant lighthouse through a sandstorm. Astronomers call this blind patch the Zone of Avoidance. But avoidance doesn't mean they gave up. It means they had to change the way they look. Infrared light can slip through dust better than visible light. Radio waves can pass through even more. And X-rays reveal something you can't miss in a galaxy cluster: blazing hot gas trapped in deep gravity wells. When scientists mapped that hidden region using these wavelengths, the sky didn't look empty anymore. It looked crowded. They found galaxies where visible surveys saw almost nothing. They found clusters packed tightly together, and they found the kind of structures that make galaxies move in groups: filaments, knots, and dense hubs, like intersections in a cosmic highway system. But here's the part that matters most. Even the galaxies and gas we can see are only the tip of the iceberg. Most of a cluster's mass is dark matter, an invisible scaffold that outweighs the stars. We don't detect it by seeing it, we detect it by what it does. It bends light, holds hot gas in place, and pulls galaxies into motion. So the Great Attractor stops being a mystery object and becomes a measurable gravitational region, a hidden concentration of matter revealed by motion and confirmed by multi-wavelength surveys. And yet, one problem remains. The speeds we measure, the way entire regions flow, can be difficult to explain with one nearby concentration alone. So what if the Great Attractor is real, but it isn't the whole story? What if the strongest pull comes from even farther away, so far that the Great Attractor is just the nearest signpost on a much larger gravitational slope? Here is where the story stops being about one hidden region and starts being about the architecture of the universe. The Great Attractor is real. There is a genuine pileup of matter in that direction, clusters of galaxies, hot gas, and a heavy load of dark matter. But when astronomers mapped galaxy motions farther and farther out, they noticed something unsettling. The flow lines do not always end at the Great Attractor. In many maps, they keep going. Think of gravity like terrain. If you drop a marble on a hillside, it will roll toward the nearest dip. But that dip might only be a small basin sitting on the side of a much larger valley. The marble slows there, swirls around, and if the slope continues, it drifts onward. That is one way to picture what some researchers think is happening here. Far beyond the Great Attractor, at distances of hundreds of millions of light years, there is another huge concentration of galaxy clusters, often discussed as one of the most massive nearby structures we know about. The Shapley concentration. It is like a brighter, deeper mass hub in the same general cosmic neighborhood, and it may contribute significantly to the motion we measure locally. In that view, the Great Attractor is not fake. It is just closer, so we feel its pull first, while an even larger structure adds its own gravitational tug from farther away. But this is also where the science gets honest and messy. Measuring these motions relies on distance estimates, and distance is one of the hardest things in astronomy. Small errors in distance can look like big errors in velocity, and that zone of avoidance still complicates the map. It is like trying to chart ocean currents while a giant island blocks your instruments. So the most accurate picture is usually this. The local flow is shaped by multiple structures: the Great Attractor region, nearby filaments and clusters, and potentially more distant mass concentrations like Shapley, all layered together into one gravitational landscape. In other words, We are not being pulled by a single monster. We are living inside a cosmic web, and gravity is the thread tension. So what does that mean for us? Are we falling towards some doom point? Or are we simply riding the natural currents of how the universe is built? That answer is where this mystery finally becomes comforting. When you hear a name like the Great Attractor, it sounds like the universe has a trap door, like we're being pulled toward a final destination. But this isn't a cosmic disaster story. It's a map-reading story. Galaxies don't sit still. On the largest scales, matter clumps into clusters. Clusters connect into filaments, and filaments form a web. Gravity turns that web into a landscape of slopes and basins. And what we call attractors are simply the low points, places where mass has piled up enough to shape the motion of everything nearby. So no, we're not being sucked in like water into a drain. Our galaxy is moving the way a leaf moves on a river, carried by currents we can't feel, through a structure too vast to imagine. The Great Attractor is one bend in that river, an important one, and beyond it, the terrain may continue into even larger valleys shaped by enormous superclusters. And that's the real wonder here. We discovered this not by seeing a giant object with our eyes, but by measuring tiny differences, slight shifts in light, subtle motion in galaxies, faint patterns in the oldest glow in the universe, and turning those measurements into a story about where we live. In a way, the Great Attractor is less like a monster in the dark, and more like a signpost pointing to our cosmic address. If you want, the next video can go even deeper into another current that may extend beyond our local basin, dark flow, where some scientists argue the motion might not stop where it's supposed to. If this mystery pulled you in, subscribe to Cosmic Vault, because the universe is full of signals, patterns, and strange, impossible facts, and we're going to chase them one by one.